Hello, everyone. Welcome. Very happy to have Andrew Obus here today, who will tell us about absolute values, product formulas, and the zeta function. And how would you like people to ask you questions?
You can just call out if you have a question in the middle, or you can ask it in the chat. It's possible that I might miss one if there's a question in the chat, but Simon, you can interrupt me if somebody types something to the chat, but kind of however you want to do it. Okay. Okay, great. All right, so thank you all for coming to this. It's great to speak to Euler's Circle. It's my first involvement at all with it, but from hearing Simon talking about it, it's a very special program with very special participants. So I'm pleased to be speaking to you all. So I'm going to talk today about absolute values, product formulas, and the zeta function, and it's mostly going to be stuff that's fairly well known. And at the end, I'm going to have a tiny little thing that I did in relationship to all of this. So let's start off over here. There's going to be kind of three parts for the talk. We're going to talk about absolute values on the rational numbers, some of which are maybe familiar, some of which are maybe not. Then we'll talk about absolute values on what are called number fields, which I'll define. And then the third thing is absolute values for non-algebraic numbers. And this is where things get kind of mysterious. And I'm not going to be able to talk about things in extreme detail here. It's going to be kind of a very high level summary. Okay, but let's at least start from what we all know. Okay, so we all know the absolute value function on Q, right? It's a function from Q to the real numbers, given by just the standard absolute value. So positive numbers go to themselves, negative numbers go to their negatives. Okay, and of course, really, this is a function on all of R, and you can even do the absolute value on complex numbers. But for now, let's consider it as a function with the domain Q. We're just going to restrict the domain. Okay, and if you think about it, if you use absolute values a lot, it turns out that it has three, particularly important properties that you use over and over again. So the first property is positivity. So that's absolute value of x is greater than or equal to 0 for all x in Q. And in particular, also that the absolute value of x is equal to 0 if and only if x is equal to 0. Okay, so an absolute value is always positive unless the absolute value is always positive unless you plug in 0, in which case you get 0. What's multiplicativity? Well, that's just if I take two numbers, if I take their product and I take the absolute values of x, y, that's just the absolute value of x times the absolute value of y. And this is true for all x and y in Q. Okay, and then the third one, which is the more subtle one, is the triangle inequality, which is a nice exercise to formally prove if you haven't done it yet. But the absolute value of x plus y is less than or equal to the absolute value of x plus the absolute value of y. You can do this in a case-by-case proof with positive and negative numbers, or there are various slicker proofs that don't require you to divide everything into cases. In any case, I'm not going to do them during this talk. Okay, so it turns out that these three properties are kind of the salient features of the absolute value function. Okay, and so you might ask, do these properties define the absolute value function? So if I take a function from Q to R that satisfies positivity and multiplicativity and the triangle inequality, then is it the standard absolute value? And you spend a little bit of time thinking about this, and the answer turns out to be clearly no. There's lots and lots of other functions that also have these properties of absolute values. So in fact, what we're going to do is instead, we're going to call any function from Q to R that satisfies the three properties, we're going to call it, an absolute value instead of the absolute value. So an absolute value is a function that satisfies these three properties, this positivity, multiplicativity, and the triangle inequality. And so we ask, are there others other than the standard one? And so I'm just going to write a couple of examples over here. So the first example would be, here's the function. You could have, absolute value of x equals, well, it could be 1 whenever x is not equal to 0, and 0 whenever x is equal to 0. Okay, so this is the so-called trivial absolute value. Okay, and it's an exercise to prove that it satisfies all three of the properties from the previous page. Okay, so this is one example of something that's definitely not the normal absolute value, but it still works. Another example would be something like, so I have to think about what kind of notation that I want to use. I could say, take the absolute value of x to be the standard absolute value of x, which I'll write x substandard. Eventually, I'll use a different notation for that, but for now, I'll just call it x substandard. So this is a definition, by the way, here, and this is a definition to be the standard absolute value, but raised to the 1/2. Okay, so you take the standard absolute value, but you take the square root of everything. So this is still going to be an absolute value, and something you can check is that if I take essentially the standard absolute value of x to the 1/2 plus the standard absolute value of y to the 1/2, that this is greater than or equal to the standard absolute value of x plus y to the 1/2. That's the only thing you really have to check. Okay. That's the only thing you really have to check. The positivity is easy, and the multiplicativity is easy. And, in fact, the 1/2 is not really special. So you can replace 1/2 with any r between 0 and 1. Okay, there's nothing special about 1/2. In fact, if you replace it with 0, you get the trivial absolute value with an appropriate definition of 0 to the 0. Okay, so far we have these different ones, but they're not necessarily so interesting. So the third class of absolute values is the one that I actually want to talk about, which is a little more interesting, and that we're going to spend a little more time talking about today. This is the so-called p-adic absolute value. Okay, and we're here, p is a prime number. Okay, and so what do you do? Well, so what's the definition? So the notation of this is going to be the absolute value with a little sub p underneath it. And the definition is, well, if a is in z, then write the prime factor, so write a as, p to the s times m, with p not dividing m. So basically take out the number of factors of p that you see, and then you define that the absolute value of a is equal to 1 over p raised to the s. Okay, so that's the definition of this p-adic absolute value. And then, of course, if a over b is in Q, you just define that the absolute value of a over b is equal to the absolute value of a divided by the absolute value of b. So this is these p-adic absolute values everywhere. Okay, so an example of this would be if you take the 5-adic absolute value of 100. Well, 100 is divisible by 5 twice. It has 2 factors of 5. You write it as 5 squared times 4. So that's going to be just 1/5 squared. Okay, or in other words, 1/25. Okay, so this is what's called the p-adic absolute value. And by the way, I think as a matter of notation, I should say here, notation, instead of the standard absolute value, we're going to write, for reasons that are maybe not so easy to explain, I won't really try to explain, I'm going to call it the absolute value with a sub-infinity. Okay, so the standard absolute value, usually call it the absolute value sub-infinity. Okay, so this is these are these 3 nice examples of absolute values. And this here is not really an example, but it's actually a family of examples. And with this p-adic absolute value, it's also a family example of examples. It turns out you can take this thing and raise it to any power between 0 and 1 also, and that will also give you an absolute value. It's going to satisfy all of the criteria that we want. Okay, so I mean, of course, the exercise here is you have to check that this is actually true. The multiplicativity is pretty easy, and the positivity is trivial. And the triangle inequality requires a little bit of work, which I'm not going to go through, but I'm going to make one little observation here, which is that, in fact, you have an even stronger triangle inequality here. You have that the p-adic absolute value of x plus y is actually less than or equal to the max of the p-adic absolute value of x and the p-adic absolute value of y. So not only is it less than or equal to the sum of the absolute values, but it's even less than or equal to the max. Okay, what this ends up translating to is basically if you have 2 numbers and you're adding them together, well, the power of p that divides their sum is at least the minimal power of p that divides both of the numbers. Okay, that turns out, if you think about it a little bit, that translates into this statement, although I'm not going to do the details here. Okay, so in fact, we have these, with these non-trivial absolute values, we have these this 2 and 3 really give you like the kind of 2 different types of absolute values. So ones like this are so-called non-Archimedean absolute values, and ones like number 2 are so-called Archimedean absolute values. Okay, and this can be defined in several equivalent ways, but one way that you can think of Archimedean absolute values is that the absolute values of integers get arbitrarily big, whereas for non-Archimedean absolute values, you see the absolute value of an integer is always going to be at most 1, no matter what the integer is, because at best, s is going to be 0, which means you're going to have 1 over p to the 0, which is going to be 1. Okay, so these are some examples of absolute values these are some examples of absolute values that you can have on the rational numbers. Okay, and so a question is kind of, is this basically everything? But before I move on to that question, are there any questions on anything I've said so far? Okay, so it turns out that this is basically everything, and it's a big enough theorem that it gets a name. So this is called Ostrovsky's theorem. So Ostrovsky's theorem says that every non-trivial absolute value on Q is equivalent to either the standard absolute value or a p-adic absolute value for some prime p. And what do I mean by equivalent? Well, I'll use the definition that if I have 2 different absolute values, one which I'll just mark with standard absolute value signs, and the other one which I'll mark with standard absolute value signs prime, that they're equivalent if there's some positive real number, so that you get one of them by raising the other one to that exponent. So for instance, the standard absolute value is equivalent to the standard absolute value raised to the 1/2. Now, often if you look this up, you'll see a different definition involving topology, but I don't want to get into topology, so I'm just going to use this as the definition, and it's equivalent to any other definition that you might see. So basically, 2 of them, you can think of them as basically being in the same family if you get one from raising the other one to some power. Okay? And maybe, you know what, just because I want to make sure I don't fall behind, I was gonna sketch the proof of Ostrovsky's theorem. Maybe I'm gonna skip that sketch for now. And then just I don't want to have to rush at the end of the talk. And so maybe I'll get to it. And then if I have extra time at the end, I can either go back and do the proof if people want to see it, or I can go into more detail about something else in the talk. Okay, so I'll just say, like, to prove Ostrovsky's theorem, you need to break it into these 2 cases. This, what I called here, this is the non-Archimedean case. And this is the Archimedean case. Okay. All right. So I think I'll skip the proof of Ostrovsky's theorem, but let's just say that, okay, that's, you know, this is everything that we have. We have the p-adic absolute values, we have the standard absolute value, and we have the trivial absolute value. And that's it. So what's the product formula for Q? Well, let's look at this. So what happens if we multiply all of the normalized absolute values of a non-zero rational number together? So let's just take an example like 12/7. Okay, well, what do we have? Well, certainly if I take the absolute value of 12/7, the infinite absolute value, which is the standard one, this is just equal to 12/7, right? Now, if I take the only primes that are going to matter here are the primes that divide 12 or 7. So I only really have to look at 3, 2, 3, and 7, right? So if I take the absolute value of 12/7 raise of the 2-adic absolute value, well, basically, I'm looking at what power of 2 divides 12 and minus what power of 2 divides 7. In this case, the power of 2 that divides 12 is exactly 2 to the 2. And so that means, if you remember the definition, that this is going to be 1 over 2 to the 2. It's going to be 1/4. Similarly, the absolute value of 12/7, the 3-adic absolute value, well, you've got 1 factor of 3 here, so it's going to be 1 over 3. And then what's the 7-adic absolute value? Well, what is this? That's the 7-adic absolute value of 12 divided by the 7-adic absolute value of 7. This has no factors of 7, so this absolute value is just going to be 1. And this has exactly one factor of 7, so it's going to be 1/7. So I'm going to get 1 over 1/7, which is going to be equal to 7. And then lastly, if I take 12 over 7p for p not equal to 2, 3, or 7, then this is just 1. Right? So overall, what happens when I multiply everything together? I get 12/7 times 1/4 times 1/3 times 7. And it's not hard to see that, the 1/4 and the 1/3 cancel out the 12, and the 7 cancels out the 7. And you end up, when you multiply all of these absolute values together, you end up getting 1. Okay? So what's the product? So I'll just say answer here is going to be 1. Okay, and you can view that as an exclamation point or a factorial, whichever you prefer. They're both correct. And so it turns out this is not a coincidence, and you may already suspect this theorem, that if you take any rational number other than 0 and you multiply all of its absolute values together, so you multiply its standard absolute value, infinity, and then you multiply all of its p-adic absolute values for every prime number p, you get 1. And notice that this is an infinite product, but you don't have to worry about like convergence of infinite products or anything weird like that, because the p-adic absolute value of any given rational number is going to be 1 for all but finitely many p, right? There's only finitely many p's that are actually going to divide the numerator or the denominator. Everywhere else, you're going to get 1. So this looks like an infinite product, but actually almost every term in this product is 1, and you're really only multiplying finitely many things. So there's no subtleties going here with this. Okay, and this is a proof as an exercise, and it's not a very difficult exercise at all. Some of you may have already done it in your heads, and in any case, like it's not one that requires any hints or anything. It's a very doable exercise. Okay, so you take any rational number other than 0, you multiply together all of its absolute values, and you're going to get 1. Okay, so this is what we call the product formula for Q. All right, any questions? Okay, so let's move on to what we call number fields. So what's a number field? A number field is a field generated by Q. You start with the rational numbers, and then you throw in finitely many algebraic numbers. So these are roots of polynomials with integer coefficients. This is what an algebraic number is. And what is a field? If you've seen some algebra, then you know what a field is. And if not, then it's just like, everything you can get from just using the standard operations of arithmetic. Everything you can get from adding, subtracting, multiplying, and dividing, starting with the rational numbers, and then throwing in whatever extra algebraic numbers you want. So the notation that we use for this is, so we could take a number like I. I is certainly an algebraic number. It's a root of the polynomial x squared plus 1. So we could take Q adjoin I, which is basically start with rational numbers, take I, and then multiply them and subtract and add and divide and get any number that you can get from that. Okay, and it turns out that's not actually very difficult. The numbers that you get are just numbers of the form a plus bi, where a and b are in Q. Okay, so these are sometimes called the Gaussian rationals. You can do something similar for Q adjoint square root of 2. That's an algebraic number because it's a root of the polynomial x squared minus 2. And so this is Q adjoint square root of 2. You can do this. And then if you want to, you can adjoin 2 algebraic numbers. You can do something like the 4th root of 7. You can do cosine of 40 degrees, which satisfies some 6th degree polynomial, with integer coefficients. So you can throw in however many algebraic numbers you want, as long as you keep it finitely many. And these are all going to be number fields. And sometimes it's not as easy to write a number. Sometimes you just have to say, here's a polynomial. We'll throw in a root of the polynomial. And that's fine. And all of these number fields we're going to think of as lying inside the complex numbers. Okay, so you've got the complex numbers. Every algebraic number is a complex number. We're just going to assume we identify it with a complex number, and all of these number fields lie inside. Okay, so Q adjoin I is a subfield of the complex numbers. Q adjoin square root of 2 is a subfield, and this is a subfield of the complex numbers. Okay, so this is what we're going to mean by a number field. And let me just write down specifically what I mentioned. So for instance, if I take Q adjoins square root of 2, what this set is it actually just ends up being the set of all numbers of the form a plus b square root of 2, where a and b are in Q. Okay. Okay, and maybe I should also just say the degree of a number field. So the degree of the number field is, so its dimension as a Q vector space. And I assume some of you have not had any linear algebra, so I don't want to actually go and define a vector space, but the point is it's just the number of parameters, right? So the degree of this number field is 2 because there's an A and a B, and the A and the B can both range through Q. Okay, so you can make that rigorous if you want to, but more or less, Q adjoin I is going to have degree 2 because it's going to be stuff that looks like A plus BI. Q adjoin square root of 2 is going to be degree 2 because it's going to look like stuff that looks like A plus B square root of 2. Let's ignore the cosine of 40 right now just because I don't want to mess it up and I didn't think carefully about what its minimal polynomial is. Q adjoin fourth root of 7 is going to have degree 4 because everything's going to look like A plus B times the fourth root of 7 plus C times the fourth root of 49 plus D times the fourth root of 343. So you're going to have 4 parameters. Okay, so that's the degree of a number field, and the degree is always going to be finite. Okay, so this is what a number field is. So we're going to talk about absolute values on number fields. So, what can they look like? So if K is a number field, we can define an absolute value, again, the same way as a function from the number field to the non-negative real numbers, just like we did on Q, as a function that satisfies the same 3 properties, right? So only 0 can go to 0. Everything else has to go to something positive. It has to be multiplicative, and it has to satisfy this triangle inequality. So one thing that you see, what happens if you restrict such an absolute value to Q? So if I have some absolute value on K, I can say, well, just what happens when I plug in just the elements of Q to that? And well, when I do that, it has to be an absolute value on Q, because obviously if it satisfies positivity and multiplicativity and triangle inequality on the whole number field K, it certainly satisfies it when the domain is restricted to this subset Q, right? So an absolute value restricted to Q is another absolute value. Okay, and so what's the upshot of this? So the upshot of this is that these things come in families, right? So if I have an absolute value defined on some number field K, well, I know that its restriction to Q is either going to be equivalent. So, so I'll just say, I know that the restriction of my absolute value to Q is equivalent to either, from Ostrowski's theorem, we know there's 3 choices: the trivial absolute value, the standard absolute value, or a p-adic absolute value for some prime p. Okay. Okay, so now there may be multiple absolute values on a number field that restrict to the same absolute value on Q. Turns out there's actually finitely many, although I'm not going to prove that. But we know that these things can't be that exotic, right? Because when we restrict them to Q, they're going to be one of these standard things, something that we have for the prime p. Okay, so let's do some examples. So let's look at Q adjoin I. So these Gaussian rational numbers, remember what this is. This is just everything of the form A plus BI with A and B in Q. Okay, so let's consider absolute values that restrict to the 5-adic valuation on Q. So one thing to remember is that 5 is 1 plus 2i times 1 minus 2i. Okay, that's a way of factoring 5 in what's called the Gaussian integers. So what can we say about the absolute value of 1 plus 2i and the absolute value of 1 minus 2i? Well, let's see things that we can do. Well, from multiplicativity, we know that, the absolute value of 1 plus 2i times the absolute value of 1 minus 2i, that this had better be equal to the absolute value of 5, which is going to be equal to 1/5, right? Because we know this restricts to the 5-adic valuation when you're actually plugging in a rational number. Right? So this is certainly going to be 1/5. So, well, what else can happen? Well, we know that this 5-adic absolute value is one of these non-Archimedean ones, which means that all natural numbers have absolute value at most 1. So another thing that you can get is that, well, the absolute value of 1 plus 2i, it turns out, I'm sweeping a little bit under the rug, but that this is going to satisfy that strong triangle inequality. Okay, that what's sometimes called the ultrametric inequality. So this is going to be less than or equal to the max of the absolute value of 1 and the absolute value of 2i. And well, the absolute value of 1 is always 1. That follows immediately from multiplicativity. And and the absolute value of 2i, well, the absolute value of 2 is going to be at most 1. In fact, the 5-adic absolute value of 2 is 1. And the absolute value of I, well, I squared equals minus 1. So the absolute value of I squared is the absolute value of minus 1, which has to be 1, which means the absolute value of I times the absolute value of I is 1, but it's got to be a positive number, which means the absolute value of I has got to be 1. So when you do that all out, we know that absolute value of 1 plus 2i had better be less than or equal to the maximum of 1 and 1. Both of these things have to have absolute value of 1. Okay, so this got to be 1. Similarly, the absolute value of 1 minus 2i is also going to be 1. Is also going to be at most 1. Okay, and so then so it turns out, so okay, so they both have absolute value at most 1, and they both multiply to 1/5. And then here I'm going to leave this as an exercise, which might be a fun thing to figure around, but you show that at least 1 of the absolute value of 1 plus 2i and the absolute value of 1 minus 2i has to be 1. Okay, one way that you can do this is look at what happens when you add them together. You see that if they both had absolute value less than 1, then their sum would have absolute value less than 1, but their sum is 2, which has absolute value 1. So that's a contradiction. Okay, so you can write that out if you want. That's the exercise. So at least one of them has to be 1, and so that means the other one is 1/5. All right, so one of these has absolute value 1, which means the other one has absolute value 1/5. And it turns out that, kind of once you make this decision, then that's basically all that there is. So this is going to be a fact, is that this is either I'll call it the quote unquote 1 plus 2i adic absolute value, or the 1 minus 2i adic absolute value. This I have not proven, but this is a fact. And by what do I mean? Basically, what's the absolute value? For instance, if you take a Gaussian integer where a plus bi, where a and b are integers, you can factor it. This turns out to have unique factorization, just like the regular integers do. And you factor out as many factors of 1 plus 2i as you have, and then you raise 5 to that number of, you raise 1/5 to that number of factors, and that's going to be the absolute value. Here, you do the same thing, but you pull out as many factors of 1 minus 2i as you can. Okay, so so it turns out that these are the only two absolute values that restrict to the 5-adic valuation on Q. And in general, if you have a given valuation on Q, there's only going to be finitely many valuations on the Gaussian integers or on any number field that restrict to that valuation. Oh, sorry, I keep saying valuation. I should be saying absolute value. Okay, so there might be a couple of choices. In this case, there are 2 choices. It's related to the idea that this number field has degree 2, but there's never going to be infinitely many choices. Okay, so every time you've got an absolute value on Q, there's only going to be finitely many ways to extend it to an absolute value on one of these number fields. Okay, questions? Okay, so what's another type? So what about Archimedean absolute values? So let's consider q square root of 2, and we want to consider absolute values that just restrict to the usual absolute value on q. What can we say about 3 plus square root of 2? This is a little bit more complicated to prove things about, so I'm not going to give as much of a justification, but I'm just going to tell you the answer right now is that there's two choices of absolute value. There's the one choice is going to be if I take the absolute value of a plus b root 2, I'm going to assume a and b are rational numbers, that this is equal to just the standard absolute value of a plus b root 2. And the second choice turns out to actually work, is that the absolute value of a plus b root 2 is equal to the standard absolute value of a minus b root 2. Okay, so for instance, so that means we could have that the absolute value of 3 plus square root of 2, we could have that this is either equal to 3 plus square root of 2 or 3 minus square root of 2. Turns out these are both, possible absolute values that something like this could have. Okay. And it turns out that these are the only two things that you can do. You can just basically take your number and just take its absolute value, or you can take kind of the conjugate of that number. In this case, it's clear what I mean by conjugate. You can take the conjugate of a plus b root 2, which is going to be a minus b root 2, and you can take that absolute value. And it turns out that both of these will satisfy all of the axioms for absolute value. Okay, again, positivity is trivial. Actually, the triangle inequality is relatively trivial once you know it for infinity. And then what's actually, not that it's hard to prove, but what's maybe actually interesting is the multiplicativity, which is basically if I have a plus b root 2 and c plus d root 2, and I take their product, then its conjugate is the same thing as taking a minus b root 2 and c minus d root 2 and taking that product. Okay. So the multiplicativity is not a difficult proof, but it's actually a very mathematically meaningful proof, and something that ends up being used in Galois theory and all sorts of abstract algebra. Okay. Okay, so it turns out we have these two choices of absolute value, and I'm not going to justify why these are the only choices. Okay. So what happens in general? So this slide is going to be a little bit cluttered, so let me just try to go through it slowly. So what are we going to have? So if SP is the set of all equivalence classes of absolute values on a number field K, so imagine we're fixing a number field K, and I'm going to take all of the different equivalence classes of absolute values, and I'm going to say, well, SP is going to be the ones that restrict to the equivalence class of the p-adic absolute value. Then, as I said, SP is finite, and there's a way of normalizing each one, by which I meaning I can pick an equivalent one. So I have a whole family of equivalent absolute values. I can pick them so that the following equation is true. So that if I take every absolute value that restricts to the p-adic absolute value, and I take some x that's in Q, there's a way of normalizing them so that if I look at all these absolute values, and I look at all of these absolute values and they're normalized appropriately, then if I multiply them all together, I should get just the standard p-adic absolute value for Q raised to this power K over Q, where this is the degree that I was talking about earlier. Okay. So before I go on to the next, let me just say, like, for the example, which we had with these 5-adic absolute values, well, what we're going to want is that the kind of 1 plus 2i-adic absolute value of 5 times the 1 minus 2i-adic absolute value of 5. Well, according to this should be the standard p-adic absolute value, 1/25th. Well, let me just write it out. This should be the 5-adic absolute value of 5 raised to the 2, which is 1/5 squared, which is 1 over 25. Okay, so there's an actual way that you can like pick kind of the right way to normalize all of these absolute values, pick the right entry from each equivalence class. I'm not going to define that, but you can do it, and you can do it in a way so that this equation here holds. Okay, so in this case, what do we want to do? What we're going to do is exactly have the absolute value of 5 here just be 1/5, and the exact absolute value of 5 here be 1/5. That's what's going to get these equations to hold. And so when you do that, it turns out that the absolute value of 1 plus 2i here is 1/5, and the absolute value of 1 minus 2i here is 1/5. Okay, so there's a way of looking at all of these equivalence classes and picking the right one. And when you do it, it ends up satisfying this equation over here when you actually plug in stuff that's in Q. Okay, so this is kind of what goes on with these non-Archimedean absolute values, the ones that restrict to a p-adic absolute value on Q. If I now do a similar thing with the set of all the absolute values on K that restrict to just the class of the standard absolute value, then again, this is finite, and there's a representative of each one, so it's not exactly parallel, saying, given by what should the absolute value of some number in your number field be? Well, it should be, you take what's called a field embedding from your number field into C. This just means, a map, a function from K into C that preserves addition and multiplication and subtraction and division. Okay, and so all of the different ways of taking these maps into C, and then you just take the standard absolute value. Sorry, this should be the standard absolute value, although what I mean now is the standard absolute value on C, not on R. And all of these different ones are the different absolute values that you have. So for our example that we had before, K was Q adjoins square root of 2, and then it turns out that you have two embeddings from K to C, right? You can have that A plus B root 2 just maps to A plus B root 2. It's kind of the identity embedding. And then you can have that A plus B root 2 maps to A minus B root 2. Okay? So these are your two choices. And so it turns out that the two different absolute values on K that restrict to the standard one are just for A plus B root 2, take the absolute value of A plus B root 2, or for A plus B root 2, take the absolute value of A minus B root 2. Okay, so those are going to be your choices. Okay, and so these will automatically be normalized correctly. Okay, so if I have a number field, what do I have? I have the trivial absolute value. I have all the stuff that restricts or in this case, real numbers would work too. But if instead of square root of 2, we had I or something like that, then we would have to be in the complex numbers. So we just do the complex numbers to make sure that we have everything. Okay. So turns out this is the set of all absolute values on number fields. And we have a product formula here too. Just like the product of all the absolute values of a rational number was equal to 1, we have the same thing on number fields. So it turns out that if you normalize all of these absolute values the correct way that we did, then if I take some, so I suppose I should say, let K be a number field. Right? Well, then if I take some element of the number field that's not 0, and I take the product of all of its absolute values, then I'm going to get 1. And I should say a little bit more about what is the index set of this product. Well, V is running over the normalized representatives of each equivalence class of absolute values as in the slide before. So all of your non-Archimedean ones, they're normalized in this correct way to make that equation work out. And for all of the Archimedean ones, they're normalized as a field embedding plus the standard absolute value on C. And the one thing that you have to do is that these Archimedean absolute values coming from complex embeddings have to be counted twice. So that's the only thing you have to do here. And so we're going to go through an example that shows, how this works. Okay. But in the end, you get this same looking product formula that the product of the absolute values of a number, you do all the absolute values normalized correctly, that product is going to be 1. And again, it's going to turn out that this infinite product is really just a finite product. Okay. So I'm not going to make any attempt to prove this. I haven't even really well defined all of these absolute values, but let me at least show you an example so you can get a sense of how this works. Okay, so let's say that we're looking at q adjoint square root of I, and we have x is going to be 1 plus 2i over 7. Okay, well, so what do we have? Let's look at the Archimedean absolute values. Well, we know that all of these come from field embeddings, right? So we have field embeddings from q of I to c, and you have two choices. You have a plus bi just goes to a plus bi, and you have a minus bi, sorry, a plus bi goes to a minus bi, complex conjugation. Turns out those are the only two things that you can do, ways that you can put these Gaussian numbers into C. And so what do you do? So the Archimedean absolute values are, well, we're either going to get that the absolute value of x is equal to just the standard absolute value of 1 plus 2i over 7, which if you do that out as a complex number, that's going to be square root of 5 over 7. Or you can have that the absolute value of x is 1 minus 2i over 7, the absolute value of 1 minus 2i over 7, which is also going to be square root of 5 over 7. And the whole point is that, in fact, with either of the absolute value of a plus bi is always equal to the absolute value of a minus bi. They're the same thing. So these two embeddings might be different embeddings, but they both give you the same absolute value, right? And so this is why we count the complex embeddings twice, because basically, technically, this is a product over all absolute values, but when you have one of these Archimedean absolute values coming from a complex embedding, it's really coming from two different embeddings, so you should count it twice. Okay, so in this product, we're going to have actually two factors of square root of 5 over 7. Okay, and then for the non-Archimedean absolute values, what are you going to have? Well, it turns out, well, for the 7-adic absolute value, it turns out that you actually, well, let's go back to our equation. What about the 7-adic? Well, if I take everything that restricts to the 7-adic absolute value, then if I plug in 7, for instance, I should get the 7-adic absolute value of 7 squared, which would be 1/49th. And it turns out there is actually only one 7-adic absolute value in the Gaussian integers. This has to do with 7 being 3 mod 4, whereas 5 is 1 mod 4. You end up getting two absolute values. So, but for 7, it turns out there's actually only one. So x, the 7-adic absolute value, is going to be 1 plus 2i, 7-adic. So we're just going to call it, by abusive notation, we'll call it the 7-adic absolute value on q adjoint I over 7 adjoint 7. And this is actually going to be 1 over 49. Okay, so this is what we're going to get for the 7-adic. Then we're going to have this 1 plus 2i adic absolute value for x. And this we already saw is going to be, the 1 plus 2i adic absolute value of 1 plus 2i over the 1 plus 2i adic absolute value of 7. 7 doesn't have any factors of 1 plus 2i. You can verify that. And we already saw that this is supposed to be 1/5. So this we're going to get 1/5 divided by 1, which is going to be 1/5. And now for all the others, so all others, you end up getting that the absolute value of x is equal to 1. So in the end, for the product formula, what do you get? You get square root of 5 over 7 times square root of 5 over 7 times, oh, sorry, this should be, sorry, that's a typo. It shouldn't be 1/49th. This is 1 over 1/49th, which is equal to 49. Right, because the 7-adic absolute value 7 is 1/49th. So square root of 5 over 7 times square root of 5 over 7 times 49 times 1 over 5, and that turns out to be equal to 1. Okay. So this is kind of like how the calculations work out. And somehow, once you've gotten the definitions correct, the proof of this is not actually that hard once you know exactly what the absolute values all are. But there's work that goes into knowing, exactly what these absolute values are. okay? But the point is, you can extend these absolute values to number fields, and you still have this product formula, and you plug in anything non-zero, you take the product of all of its absolute values, you're always going to get 1. Okay. Any questions? Okay, so this is all, maybe this is probably new to some people, but it's maybe at least a little down to earth and it's not that weird. Okay, so let's get into the weird stuff for the last 10 or 15 minutes of the talk. Okay, so product formulas for non-algebraic numbers, right? So every algebraic number we've been talking about, remember that means it's the root of a polynomial with integer coefficients. It lives inside some number fields, so that number field will have a product formula, and for every algebraic number, there's some sort of product formula where you take the product of all of its absolute values, you're going to get 1. So the question is, could there be a product formula for non-algebraic numbers? Well, okay, I mean, I could take a number like pi or e or something. These are non-algebraic numbers. That's actually not easy to prove, to the point where I certainly have not memorized the proof of these things. But it's true, they're non-algebraic numbers. And I mean, they have standard algebraic numbers. You could say, okay, the absolute value of pi, sorry, they have standard absolute values. You could say, okay, the absolute value of pi is pi, but these things, they live in the real numbers, or really they live in the complex numbers. You could have ipi or, e plus ipi or whatever weird numbers you want to make out of these things. And if you want to just say, like, what are all of the absolute values that you can have on C? Well, it turns out there's just way, 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 way too many of them. Okay, it's not like these number fields where the absolute values come in kind of these nice families, and you can really kind of get your hands on knowing exactly what they are. If you just say, what's an absolute value on C? Well, there's the standard one, and then there's a bunch of other, like, completely, totally weird ones. Okay, so it's very hard to keep track of these. You can't really catalog all of the absolute values on C. And then there's also tons and tons of transcendental numbers, which means a non-algebraic is the same thing as transcendental. So there's tons of these. So to just kind of like try to write down some product formula where you say, well, I'll take every absolute value, somehow take an appropriate equivalence, an appropriate representative of its equivalence class, and then multiply all of these together for some transcendental number, you're just going to get garbage. Okay, there's kind of no way, no naive way of just making this work out. But it turns out that there are certain special complex numbers which are called periods. Which are more or less numbers whose real and complex parts are definite integrals of algebraic functions over regions bounded by algebraic functions. So they could be double integrals or triple integrals or whatever. So for instance, pi is a period, because you can write pi as the integral from -1 to 1 of 2 times square root of 1 minus x squared dx. Right? I mean, if without the 2, that would just be the area of the upper unit semicircle, which would have area 1/2 pi. So I can multiply it by 2 to get, pi. And this is an algebraic function, meaning it's given by, roots and stuff of polynomials. Really, it means that, it satisfies a polynomial in T where the coefficients are polynomials in X. But in general, anything you can write with roots and polynomials and stuff is going to be an algebraic function. There's more stuff than that. And then the regions that are bounded, well, -1 and 1 are standard complex numbers. Are constants, so they're algebraic functions also. I guess these should be really, I should say that everything has to be defined over Q. Otherwise, you could do trivial things like saying that, pi is the integral of pi from 0 to 1. So you don't want that. You want the coefficients to all lie in Q. Okay, but so pi is one of these numbers that's a period. So it's a transcendental number, but it is a period. And of course, 2 pi is also a period, because you could just replace this 2 with a 4. And then 2 pi I is also a period, because you're just looking at the real and complex parts. So I want to talk about what could a product formula possibly mean for 2 pi I. Okay, and so the next couple slides will basically be a bunch of black magic that's going to give you a product formula for 2 pi I. What does it mean to take all the absolute values of 2 pi I? But trust me that there is actual math behind all of this stuff that can be made rigorous. Okay, so all right, so what about the absolute values of 2 pi I? Well, here's one of them. I can take the standard absolute value of 2 pi I. in the complex numbers, and that's going to give me 2 pi. Okay, so if we want a product formula, kind of like what we've had before, well, what do we have? We have our standard absolute values. This one is, okay, 2 pi. And then we have these p-adic absolute values, right? So what the heck is going to be the p-adic? I shouldn't say valuation. Sorry, I was on autopilot writing this. Let me say absolute value. So what is the p-adic absolute value of 2 pi I? And that's a little weird because for a prime p, you can't really talk about, you don't want to just say that, oh, well, it's divisible by 2, because what does divisibility even mean when you're throwing around transcendental numbers like pi? In any case, the wrong answer is that, well, the 2-adic absolute value is 1/2, and all the other primes, their absolute value is 1. That's kind of untenable. So it turns out there's actually a good case to be made for the calculation that the p-adic absolute value of 2 pi I is p to the 1 over 1 minus p. Okay, so that 2 pi I, how many times does p divide it? It actually divides it 1 over p minus 1 times. And justifying this will go well beyond the scope of the talk, so I'm not going to really be able to justify it, but it comes in some sense from taking, if you know any complex analysis, which I assume maybe not many of you do, but it's Euler circle, so there may be some people who do, that integrating dx over x over the unit circle, taking a contour integral in complex numbers, that's going to give you 2 pi I, and it turns out there's a p-adic analog of that, and it gives you something that's called a p-adic period, and that period looks like p to the that period looks like p to the 1 over p minus 1. Okay, so in any case, there's a good there is a good solid, you're on solid ground if you want to say that the p-adic absolute value of 2 pi I is this. It's p to the 1 over 1 minus p. Okay, so the 2-adic absolute value in that case would be 2 to the 1/2, be square root of 2. Oh, sorry, 2 to the negative 1/2 would be 1 over square root of 2. Okay. So, all right, so we have absolute values. So now we want a product formula. So we have to somehow multiply all these things together. So a product formula should be something like, well, if we take the Archimedean absolute value, that was just the standard one, that was 2 pi, and then we multiply all of the non-Archimedean absolute values, that's p to the 1 over 1 minus p, somehow we should be able to take this infinite product and get 1. And now we're in some trouble, right? Because this product is not one of these easy ones we had before where actually all but finitely many terms were 1 and you just had to do a finite product. Here, you've got a bunch of terms that are not 1. You've got infinitely many. None of these terms are 1, right? So you're trying to multiply together some infinite numbers. And it turns out this is even worse than that because this doesn't even converge. So since maybe people don't really know so much about convergence of infinite products, let's change everything to a sum. So let's just take the log of both sides, where I implicitly mean the natural log, but the base doesn't really matter. So with logarithms, I could say that, well, log of 2, what we want to show, if we want to show this, we want to show that log of 2 pi minus the sum over all primes of 1 over p minus 1 times log of p, right? The minus is what's changing the 1 minus p to the p minus 1. We want to show that this sum is equal to log of 1, which is 0. And from some basic calculus, you can show that this is a divergent series. Okay, so this expression proving that this equals 0 is meaningless unless you give it a meaning. Okay, this is a divergent series, and you can't make any meaning of this statement. So how do we get a product formula? Well, it turns out that we can use something called the Riemann Zeta function to come help us. So the Riemann Zeta function is this function zeta of s equals the sum from n equals 1 to infinity of 1 over n to the s. So, 1 plus 1 over 2 to the s plus 1 over 3 to the s, and so on. So there's various nice facts about the Riemann Zeta function. So zeta 2, which is 1 plus 1/4 plus 1/9, and so on. This turns out to be pi squared over 6. If s is equal to 1, this thing diverges. You have 1 plus 1/2 plus 1/3 plus 1/4. It's the harmonic series. This diverges. And so it turns out that, and you can even make sense of this for s a complex number, okay? So Euler, good to be able to quote Euler in an Euler circle lecture. So he showed that you can actually write this zeta function as a product over all prime numbers of this, and what of 1 minus 1 over p to the s to the -1, you need a certain range. So if you're going to look at s to be a complex number here, you need the real part of s to be greater than 1 for this to make sense. But we're being fast and loose here, okay? So and how does this work, by the way? This is 1 over 1 minus 1 over p to the s. So you can expand that out as a geometric series, and then if you collect up all the terms, it turns out that you'll get exactly this series. So once you have that, then you have to be a little bit careful about convergence issues because you're talking about infinite products. But in any case, they can be dealt with. And so we have this Riemann zeta function, and it can look like this. Okay, so what does that have to do with our sum here that we want to evaluate? Well, I'm just going to rewrite this. I'm just copying the same line over here. Well, if this is Riemann zeta function of s, well then, what the hell? Let's just take its logarithmic derivative. So let's take its derivative with respect to s and divide by the function itself, which by the chain rule is the same thing as taking the log of the zeta function and then taking its derivative. So what do you get? Well, the log is nice because the -1 comes down here, and then the product becomes a sum, and you get the log of 1 minus 1 over p to the s prime. And so it turns out that if you try to just do this and plug in s equals 1, which you can't really do because everything diverges, but why not just try to do it anyway? If you just kind of like do this with, just completely mechanically, and you plug in s equals 1, it's an exercise that you can find out that zeta prime of 1 over zeta of 1 is going to turn out to be equal to this sum of 1 over p minus 1 log p. Now, where have we seen that before? Let's go back here. Well, 1 over p minus 1 log p. That's pretty nice, right? So maybe this infinite sum should have something to do with doing this, taking this logarithmic derivative of the zeta function and then plugging in some number that you have no right to plug in at all, okay? And so now this zeta function is a function on the complex numbers, and it turns out it has something that's called a functional equation in analytic continuation, which basically is a way that you're allowed to extend the domain of a function on the complex numbers, even when plugging in certain things into the domain don't make sense. So in this case, it only really makes sense to plug in real numbers whose real parts are greater than 1, but actually you can plug in a bunch of other stuff also and paste everything together. It gives what's called an analytic function. But basically, there's a way of like taking complex valued functions of complex numbers and extending the domains larger than what you think you'd be able to plug in. And it turns out that when you do this, you have this nice symmetry with the Riemann zeta function. You have this nice symmetry where s goes back and forth to 1 minus s. So from this, you can basically say that zeta prime of 1 over zeta of 1 is the same thing as zeta prime of 0 over zeta of 0. And I have this approximate because that's not exactly right. There's some pi's and some gammas and some extra factors there, but we're playing super fast and loose, so we're just going to ignore them all. And then it turns out that if you evaluate this zeta prime of 0 over zeta of 0, you get log of 2 pi. Okay? So what's going on here? So zeta prime of 1 over zeta of 1, for our purposes, is log of 2 pi. What we've seen when we plug in 1 into this formal series is that it's also the sum of 1 over p minus 1 log p. So, well, these two things are the same, which means that the difference of log of 2 pi and this 1 over p minus 1 log p is going to be 0. So this is, again, totally nuts, and you shouldn't believe any of it. I mean, you're plugging in things that you're not allowed to plug in. You're extending domains of functions that you're not allowed to extend. You're using functional equations that I haven't proven for you, and you're not even really using the functional equation. You're kind of ignoring some factors in it, okay? But if you do all of these things, you do get this provocative result that log of 2 pi minus 1 over p minus 1 log p is 0. Oh, yeah, and you also have to believe me that the p-adic absolute value of 2 pi I is p to the 1 over 1 minus p. Okay, so there's a lot of weird stuff going on, okay? But if you accept all of this, you do get the product formula. And it turns out, so it's my last slide, it turns out that Pierre Comtes, French mathematician in '93, conjectured a similar product formula, not just for 2 pi I, but for all numbers that are so-called periods of abelian varieties with complex multiplication. Okay, so these are special types of periods. They're periods like what we had before, but some very special things. So in particular, what's the conjecture? As I should say conjecturally, that each such number has an Archimedean absolute value and a bunch of p-adic absolute values. And when you multiply them all together, you should get 1. Or logarithmically, if you take the log of the Archimedean absolute value plus the log of all these p-adic absolute values, you should get 0. And so Colmez showed that for a subfamily of these periods, so these are periods where the complex multiplication field is what's called abelian, that he wasn't able to prove that this was equal to 0, but he was able to prove that it was equal to c log of 2 for some rational number c. Okay, so it's almost 0. There's something going on with the 2-adic valuation that was hard to pin down. Everything else kind of vanished. And so my contribution to this is that I proved that c is equal to 0 in this case. So that in fact this product formula, or really the sum formula, when you take the logarithm, holds for these periods. Okay, so if anything, maybe this will encourage you to learn some complex analysis or some Galois theory or some p-adic analysis, all of which go into these results. And if not, then at the very least, this product formula over Q is hopefully a nice down-to-earth thing that you can take away from the talk. Okay, so thank you very much for your attention. It's been a pleasure.
Thanks for a great talk. So, are there any questions now? Well, okay, so if there are no questions, then let's thank Andrew again, and that concludes this part of the class.